In this video, we're going to take a look at section 6.1 on Introduction to Radicals. All right, so this is the definition of what radical notation means. If a equals b to the n power, then this is read as the nth root of a is equal to b. So let's put some numbers in here to make some sense of this definition. So for example, let's put like, I don't know, let's say 5 squared here, right? So b is 5, n is 2. 5 squared is equal to 25, right? So 25 is 5 squared. Then what that means is if we take these same numbers and place them over here in this formula, we'll have the radical symbol. The 2 is the value for n, so the 2 would go here. A is the 25, so the 25 would go in here. And the b is 5. And so what we would get is the second root of 25 is equal to 5. What this means, what this is measuring is the origin. So the word root here literally is like your heritage or your ancestral roots, right? We use that phrase sometimes. That's kind of the meaning here in mathematics. It's talking about the origin of the number 25, the roots. Where does it come from? In terms of things being raised to the second power. So how do we get 25 by raising something to the second power? We get it by raising 5 to the second power, right? So the question this is asking is what number, when squared, right, when it's raised to the second power, gives you 25? The origin of 25 in terms of powers of 2. That's what a square root is. And we know 5 to the second power is what gives me 25, and so the answer here is 5. All right, now I'm calling this a second root, and I'm putting the number 2 here, but for second roots, we actually have a special name for that, and we have a little bit of a special notation for it. So we actually don't call these second roots, we call these square roots. So instead of calling it a second root, let's call it a square root. And because it's a square root, that's the default option for these radicals. So we don't actually have to write the 2 there. If the number is missing from this area, it's assumed to be a square root. That's sort of the basic one that we assume it to be if the number is not there to indicate it. So really this would typically be written like this, without the 2 written there. And so we are to assume that means it's a second root, which we're going to call square root. And so the square root of 25 is equal to 5, which at this point, most students already know that as a fact. But and this just kind of confirms it. Let's look at one more example real quick of this, but let's not do a square root this time. Let's do like 2 to the third power, for example. 2 to the third power is equal to 8. So if we take these numbers and plug them in over here, what we're going to end up getting is radical symbol. This time we'll use a 3 because that's the power that's here. So that's the root we'll talk about over here. And 8 will go inside of the radical symbol, and then 2 is going to go on the right-hand side. And so this is read as the cube root of 8. And again, what it's asking for the origin of the number 8, right? What are the roots of 8? What are its roots in terms of powers of 3, right? In other words, what number raised to the third power would give me 8? Whatever that number is, that's the answer I'm looking for. And the answer is 2, right? 2 to the third power gives me 8. And so the origin of the number 8 in terms of powers of 3 is 2. That's how you get 8 from raising things to the third power. All right, and so the answer is 2 here. So the cube root of 8 would be 2. All right, let's look at some more examples. Oh, okay, I think I just totally erased everything I just wrote. That's crazy. Good thing I've captured it on video. So I hit the wrong button by accident. Okay. So we want to simplify this. So we're looking for the cube root. So this, again, you could call it a third root. I didn't think about mentioning that a moment ago. But the special name we have for this is cube root. Nobody calls it a third root. So we're looking for the cube root of 27, which means we're looking for the origin of the number 27 from things being raised to the third power. In other words, what number raised to the third power would give me 27? And you'll want to start to pick up on these facts because it'll help with doing these problems. And I have at the end of the video, I'll have a list of ones I think you should memorize to help you get through this chapter. You could just try guess and check. You know, you might say, okay, well, what's 2 to the third power? Well, that's 8. That doesn't give me 27. What about 3 to the third power? Well, that means 3 times 3 times 3. If you multiply that out, you actually do get 27. So the answer here is 3. 3 to the third power is what gives me 27. That's the origin of the number 27 in terms of powers of 3. And so the answer here is 3. Right? So the origin of the number 27 from things being raised to the third power is the number 3. All right, this one is one that you probably wouldn't bother to memorize. So the list I'm going to give you at the end of the video would not have this on the list. So this one, we just have to kind of figure out by trial and error. We're looking for a number that when it's raised to the 4th power, right? This is the 4th root of 2,401. So what number raised to the 4th power gives me 2,401? That's what we're looking for here. That's the origin of the number 2,401 from things being raised to the 4th power. So I'm not really sure what that is, so let's just start with 2. 2 to the 4th power, I actually know what that one is. It's 16. 3 to the 4th power is another one that's good to memorize. It's 81. But then that's kind of where I stop memorizing them. So 4 to the 4th power, I would most likely want to use my calculator. I think I know what this is. It's going to be 16 times 16, which is a 256. So still not very close to that 2,401, but you see these jump up pretty quickly, right? 5 to the 4th power is going to be 625, so that doesn't quite get me to that big of a number. Let's try 6 to the 4th power. This one I really have no clue what it is. So let me see if I can find, I don't really have a calculator, so I guess I'll have to use my phone again. All right. Calculator. And I'll have to tilt it sideways to get the exponent button on there. So we have 6 raised to the, well, that's not it, raised to the 4th power. That's 1,296. So we're getting pretty close, right? 1,296. So let's try 7 to the 4th power. I think this is going to be the one, actually. 7 raised to the 4th power is 2,401. All right. So we finally get there. So it's 7 raised to the 4th power that gives me 2,401. And so the answer here is 7. That's the origin of 2,401 from things being raised to the 4th power. All right, so we have a couple more examples here, I believe. So here we have a negative sign. Now, negatives and radicals, there is a little bit of difficulty there with resolving those. But the difficulty actually doesn't show up here. It shows up for different situations. All right, so what we're looking for here is a number that when I raise it to the 3rd power will give me negative 125. So again, we can go back and look at numbers raised to the 3rd power. I don't know if we got that far last time, so I guess let's just start a new list here. All right, so we know 2 to the 3rd power is 8. We did that one last time on the previous screen. 3 to the 3rd power is 27. That's as far as we got last time. 4 to the 3rd power is 64. This is another one that I just have memorized off the top of my head. And this is another one I have memorized too. 5 to the 3rd power is 125. So that's what we're looking for. But we want it to be negative. So the question is, if I put a negative here with the 5, and I raise negative 5 to the 3rd power, will that give me negative 125? So remember, to the 3rd power means we're going to multiply this thing to itself 3 times. 5 times 5 times 5 gives me the 125. Negative times a negative times a negative. Well, 2 negatives together become positive, and then multiplying that by another negative means this answer will indeed come out negative. So the answer we're looking for here is negative 5. Negative 5 to the 3rd power gives me negative 125. And so the negative sign isn't really an issue for cube roots, because with powers of 3, when we raise a negative number to the 3rd power, the answer still comes out negative. And so it's like the negative sign, the way I think of it is it just kind of passes right through. The cube root doesn't have any issues, or there's no conflict here between cube roots and negatives. The negatives just go to the answer, basically. And so I kind of think of this as the cube root of 125 is 5, and the negative sign just will pass right through on that. Okay, when it's an even root, like when it's a square root or a fourth root, then the negative sign causes us some problems, and we'll have to talk about that at some point in this chapter. I don't know if it's in this section or not. But for cube roots, fifth roots, odd roots, any kind of odd number, negative signs are not an issue inside the radical. The answer will just be negative to match it. Right? Okay, so same thing's going to happen here. So what we're looking for is what number. Now, we're going to learn ways of simplifying radicals with fractions later in the chapter. But at this point, we haven't introduced those methods yet. And so we're looking for a number that when it's raised to the third power will give me negative 1 over 64. Now, if we go back to our previous list, we saw here that for powers of 3, 4 to the third power gives you 64. What I want to get is 1 over 64. So what does that is 1/4, right? 4 to the third power gives you 64. 1 over 4 to the third power gives you 1 over 64. Right? You can check that out if you want by raising it to the third power. We know how to simplify this. You apply the power to the top and bottom of the fraction. You get 1 to the third power over 4 to the third power. 1 to the third power is still 1. 4 to the third power is 64. But we also want to get a negative result here, which means the 1/4 needs to be negative. And that way, let's say we keep the negative with the 1. This becomes negative 1 to the third power, which will be negative 1. Just like we talked about on the previous example. Because when you multiply negative to itself 3 times, the answer will still come out negative. And so the number we're looking for here, that when it gets raised to the third power gives me the negative 1 over 64, is negative 1/4. And so that's my answer here, negative 1/4. And like I said, there are sort of faster methods for evaluating this that we will learn later. But for now, this is the way we're supposed to approach it. Okay, another way you can think of radicals is that they cancel out powers as long as the numbers match. So, for example, well, this is the way I like it. This is not really an example. This is just the rule. Nth roots cancel out powers of n. So square roots cancel out powers of 2. Cube roots cancel out powers of 3. Fourth roots cancel out powers of 4. Fifth roots cancel out powers of 5. All right, so the same thing's going to happen here. So a ninth root cancels out powers of 9. And so this ninth root is going to cancel out that power of 9, and my answer is just going to be y. All right. Again, if you want to think of it this way, we're looking for, you could go back to how we were doing the previous problem, right? What number, or not this case number, but what variable raised to the 9th power is going to give me y to the 9th power? Right? I mean, that's what we're looking for here, right? So what thing, that's what a 9th root is asking, what thing raised to the 9th power gives you this result? And what we need here in this question mark is a y. Y raised to the 9th power will give me y to the 9th power. So the answer is just y. All right. So, all right. Now this, notice the directions have this extra, how do you say, condition attached to it. So find the following. Assume that the letter can represent any real number. And that's the same thing we're seeing here. Now, assuming that y can represent any real number is not an issue here. It becomes an issue for this problem, though. So if we follow the same logic down here that we used up here, using this idea that fourth roots cancel out powers of 4, that's exactly what happens here, right? So we have the fourth root of x to the 4th power, and we just talked about how fourth roots cancel out powers of 4. So this fourth root cancels out this power of 4, and we just get x. You can also think of it like this, right? What number raised to the 4th power, that's what a fourth root is asking, gives us x to the 4th power. So what we're missing here is an x. X to the 4th power gives me x to the 4th power. Right? And so the answer here is x. So this is what we're asserting. The fourth root of x to the 4th power is equal to x. And this is not an equation, like a conditional equation where this might be true or might not be true, depending on what you plug in for x. This is supposed to be an equivalency, that this thing always equals this thing, no matter what. The fourth root of x to the fourth power is the same thing as x, no matter what number is getting plugged in. So let's test that theory. Let's plug some numbers in for x and see if it does actually match up, if the left-hand side actually does match up to the right-hand side every time. So we'll plug in a number. Let's, for example, plug in the number 3, right? So I'll plug in 3 for x on both sides of this, right? So we'll get the fourth root of 3 to the fourth power equals 3. 3 to the fourth power is 81. So we get the fourth root of 81 is equal to 3, which is true, right? The fourth root of 81 is 3. It's asking what number raised to the fourth power gives me 81. The answer here is 3. 3 to the fourth power gives you 81. So I'm out of room here for this one because I want to save room for a different number over here. But this is equal to 3. I'm trying to think how I could write that here. So this is going to give me 3 equals 3. I'll just write it over here. So this does equal 3. So I get 3 equals 3, which is true, right? The left-hand side matches up to the right-hand side, just like we are asserting up here. But if you try -3, for example, let's plug -3 in here. We'll get the fourth root of -3 to the fourth power equals the right-hand side here will be -3. So when I simplify the left-hand side, what's going to happen is the -3 to the fourth power, that's kind of a weird bracket there, but that's going to give me 81, positive 81, right? Because when you raise a negative number to an even power, the answer comes out positive because you're multiplying a negative number to itself an even number of times. So all the negative signs cancel each other out and you get a positive answer. And then the fourth root of 81 we just talked about over here is 3. So we're going to get 3 equals the right-hand side, which is -3, which is not true, right? So these are actually not completely equivalent at all times. This is only true when x is a positive number. So if I'm plugging in positive numbers for x, yes, the left-hand side matches the right-hand side. It works out fine every time. But if I plug in a negative number for x, this side is always positive, even for negative numbers being plugged in for x. This side will be negative if I plug in a negative number for x. So this side is always positive. This side is not always positive. So they're really not equivalent to each other if they have this difference, this characteristic that's different between them, right? One side's always positive, the other side isn't always positive. It depends what you're plugging in for x. So you can't have two things be equivalent when they have that discrepancy, which means we need to fix that discrepancy to make them equivalent to each other. So if the left-hand side is always going to be positive, no matter what I plug in for x, I need to make sure the right-hand side will also always be positive no matter what I plug in for x. And so when I'm doing my face-to-face class, I will ask my students, what could I do to the right-hand side to guarantee that it will always come out positive? And they'll brainstorm different ideas, and usually they'll give me a couple of wrong answers like, well, you could square it. You could raise it to the second power. Yes, I could. That would make sure it comes out positive, but it will also change the number here. And the number is not the problem. I want this to be a 3. I just don't want the negative to be here. And so if I square it, it's going to change it to a 9. And so now the numbers won't match up. So you want to leave the number the same, but just make sure that it always comes out positive. And we have seen something that does this in this course, and it is the absolute value, right? The absolute value symbol always makes numbers positive. It doesn't change the number. It keeps the number the same, but it's like a filter to make sure that the answer is always coming out positive. So to make these equivalent to each other, I will need to put an absolute value on the x. And now, when I go through this exercise again, the absolute value of 3 is still 3, so this still works. But here, when I apply the absolute value of -3 is going to be positive 3. And now I fix this one too. So now these will match up to each other, right? And so now they will be true, right? You'll get 3 on the left-hand side, 3 on the right-hand side. So now it's true for negative numbers as well. And so that's what this piece of the directions is about. Assume x can be any real number, because if we only assume x is positive, then we don't need the absolute value, right? It wouldn't be necessary, because if we're only using positive numbers for x, we don't need an absolute value to make the numbers positive. But if we're assuming that x can be any real number, then this doesn't work for negative numbers, so we need to put an absolute value to make it work for all numbers. All right, so the correct answer here, what you have to type on Math Excel, is not just x, but you'll have to type in the absolute value of x. Now, you might say, okay, that's no big deal. So when we're dealing with variables, just put an absolute value on the variables. That isn't exactly true either, because we did not need an absolute value for this one. If you put an absolute value on the y here, that's wrong, because here, this one isn't always positive, right? Y to the 9th power will still come out negative if you plug in a negative number for y. And taking the 9th root of a negative number will be a negative answer. So if this side isn't always positive, we don't want to make this side always positive. So we actually have to be selective in when we apply that absolute value. So here's, again, I'm trying to explain the math behind it, but if you want me to boil it down to a rule for you to remember, this is the rule. That if the root is an odd number, like this is a 9th root, you do not use an absolute value on your answer for these variables. So odd roots, no absolute value. If you have an even root, then you need to use an absolute value on your answer. Now, there are actually some exceptions to that, but I don't think any of those problems are given in this textbook. We had a textbook previously. So the example I'm thinking of is this. If you do the 4th root of x squared, sorry, I got that backwards, sorry. Let me flip those numbers around. Let's do the square root of x to the 4th power, right? Now that's an even root, right? It's an invisible 2 here. So that's an even root, which means you should be on alert to use the absolute value. But when you simplify this, and we're going to talk about how to simplify this later, like in the next section, this comes out as x squared. You actually don't need absolute value on this because x squared already comes out positive anyways. And so you only need an absolute value if you're dealing with an even root and the answer doesn't have an even exponent. Like this is x to the 1st power, right? This is x to the 1st power here. And so that's an odd exponent. So you need an absolute value to guarantee that to come out positive. This is already going to come out positive. It's already guaranteed. So an absolute value is unnecessary here and would be wrong to use. So I don't think this situation comes up in this textbook though. So I don't think you're going to have to worry about that. So I think you're safe to assume if there's an odd root, do not use an absolute value. And if there is an even root, you should put an absolute value on your variables. If it's just numbers like we were doing before, right? So if we go back to these previous problems that we were looking at, it's been a while since we did an even one, but like this one, you don't need an absolute value on the 7 because 7's already positive, right? There, absolute value of 7 is just going to be 7 again. So for numbers, you don't need to use an absolute value. Just for variables, if it's an even root, like a square root, a 4th root, a 6th root. All right, so while I've gone out of my way to explain all of that, there's only a couple of problems on the homework where this is going to be relevant. Maybe one problem on the test where that's going to be relevant. And even if you forget the absolute value, it's not like you're going to get complete 0 on the problem. I'd still give you partial credit for getting the other part of the answer right. So I wouldn't stress out about it too much. It's not going to be that big of a component to Chapter 6. All right. So let's look at a couple of more examples and then we'll be done. So here we're looking for something, an expression, that when it's raised to the 3rd power, because it's a cube root, so we want something when it's raised to the 3rd power, will equal negative 27x to the 3rd power. Again, we are going to learn a shortcut for simplifying this later in Chapter 6, but for 6.1, the only method we have is what we're doing right now. What raised to the 3rd power will match up to this? Now, to get the 27, what number to the 3rd power gives me 27? It's going to be a 3. Right? 3 to the 3rd power will give me the 27. To get the negative sign, I will need a negative here, because when I raise a negative number to the 3rd power, the answer will still come out negative. And to get the x to the 3rd power, I'm going to need an x here with the 3, so that when this gets raised to the 3rd power, that will give me x to the 3rd power. So this to the 3rd power gives me negative 27x to the 3rd power. All right, let's test that out. Right? So if I take this, raise it to the 3rd power, we learned in Chapter 4 you can distribute the exponent here. And so I'll get negative 3 to the 3rd power, and then x to the 3rd power. Negative 3 to the 3rd power is going to be negative 27x to the 3rd power, which is what we were looking for. Right? So the answer here is negative 3x. That's the thing that when it gets raised to the third power will match up to this. All right. Now here it doesn't have it in the directions, but because it's an odd root, I do not need absolute value on my variable. All right. It's an odd root, so absolute value is just not necessary. Here, this is a square root, right? The number, there's no number here in this area, which means it's a square root. It's an invisible 2. So I'm looking for a number that when it gets squared will give me 4x squared. Right? So not just, I keep saying a number when it's squared, but I should say an expression when it's squared that will equal 4x squared. So to get the 4, I would need a 2 here, right? 2 squared will give me 4. And to get the x squared, I would need an x here. X squared is going to give me x squared. So, you know, again, we can test this out. 2x to the second power. Right? Again, we distribute the exponent, so we get 2 squared, x squared. 2 squared gives me 4, and then the x squared just copies down, so it matches up to the thing that I want it to match up to. And so the answer here is going to be this. It's going to be 2x. 2x is the thing that we want to square to give us that expression. Because that's an even root, we will need to put an absolute value on the variable. You don't need to put it on the number. The number's fine. It just needs to be on the variable x. Right? And so my answer is going to be 2 times the absolute value of x here. So anytime you see this in the directions, assume that x can represent any real number, you need to be on alert for applying an absolute value to those variables. It even says here, use absolute value notation when necessary. Right. It didn't say it up here, so then I think it's safe to keep that off your radar. But when it does say it, you need to consider it. I wouldn't automatically assume, oh, if it says that, I need to put an absolute value, because we saw in this example, right? Here, it says assume the letter can represent any real number, but absolute value still wasn't necessary for this answer. So don't just automatically put an absolute value when you see that, but think about whether it should be applied or not. And like I said, the easiest way I think to tell is it an odd root or is it an even root? If it's an odd root, no absolute value. If it's an even root, then yes, you should put an absolute value. All right. The last example I have here, and there's just a couple of these problems at the end of section 6.1, and we won't really see this very often from this point on, but determine the domain of the function. So it didn't really come up, I guess, in the examples that we were doing, but we saw negative numbers inside of cube roots, and we talked about how that's really not a problem. The negative sign just copies over to the answer, basically. But that doesn't happen with square roots. So if we have the square root of, let's say, -9, we're looking for a number that when it gets squared will equal -9. Sorry, that came out kind of weird. Let's try that again. Equals -9. And so you might try -3, right? Maybe -3 to the second power gives me -9. Well, -3 to the second power actually equals +9, right? Because when you square a negative, that's -3 times -3. Negative times a negative will make it positive. So we actually cannot match that negative sign. We can get 9, but we can't get the negative sign from squaring a number. And so the conclusion we're going to draw for now later in the course, we actually will have a way of resolving this. But for now, we actually don't have a method for dealing with this situation. So what we're going to say, this is not a real number. So if you get a negative inside of a square root, it doesn't resolve. The answer is not a real number. And like I said, we're going to learn how to resolve it later, but for now, it just doesn't resolve. Which means we want to avoid that here. We don't want to plug in a number for x that makes this come out negative, because then there's no resolution to it. So for example, if I plug in x equals 0 here, I'll get the square root of 5 times 0 minus 4. That's going to be the square root of -4, which has no resolution. This is not a real number, again, because it's a negative. I can't square a number and have it come out as a negative answer. So there's no answer to this. So we want to avoid that. So the domain, remember, we talked about domain back in like chapter 2 or 3. The domain is the set of values that I'm allowed to plug in for x. I do not want to plug in a value for x that doesn't resolve to an answer. So 0 is actually off limits for this equation because it doesn't provide a resolution when you plug it into the function. So 0 is not part of the domain. 0 is not a valid choice for x. Now 1 is okay. If I plug in 1 here, I get 5 minus 4, which is 1. The square root of 1 is 1. It works out. We get a resolution. It has an answer. So 1 is okay, but 0 is not okay. So there's some threshold here where we transition from numbers that are okay to plug into this function to numbers that are not okay. And we want to find where that line is. Where do we reach that threshold where the numbers stop working and stop having a resolution when you try to simplify it? And to find that, here's how you want to do it. You want to take whatever expression is inside the radical, which is 5x minus 4. And what has to be true about this for it to have a resolution is it has to be positive. Or it could be as low as 0, right? So if I get 0 in my square root, the square root of 0 is 0. It has a resolution. But if I get a negative in my square root, it doesn't have a resolution, right? So the threshold here is 0. As long as I can keep this result to 0 or more, as long as it's positive, the square root produces a resolution for, I'm sorry, I keep saying the word resolution. I don't know another way to say it. It gives you an answer as long as this thing comes out positive, which means bigger than 0, right? This is how we say positive in mathematics. So as long as 5x minus 4 comes out positive, you're going to get an answer out of this and it's going to work out. It's going to be good. If it comes out negative, that's when you have a problem. So let's find out for what values of x this will stay positive by setting up this inequality. So I'm going to take 5x minus 4, set it greater than or equal to 0, and then I can solve it for x to find out what I can choose for x to satisfy this inequality so that this always comes out positive. So solve this for x by adding 4 to both sides. You'll get 5x is greater than or equal to 4. Then you divide by 5 on both sides to get x by itself. And you get x has to be greater than or equal to 4/5. Right? So if I want this to produce an answer that, how do I want to say it? If I want this to produce a result that gives me an answer that actually produces a number, then I have to choose values for x that are bigger than 4/5. If I choose anything smaller than 4/5, this is going to come out negative, and the square root of a negative doesn't produce an answer. It doesn't resolve to a solution. And so this is my domain. These are the numbers that I can choose for x for this function so that it works out to give me an answer that I can use. All right, and so we want to write this in interval notation. So think of this on the real number line. We have 0 here, and here's 4/5 is positive, so it's just to the right of 0. This is supposed to be a 4 right here. Greater than 4/5 is going to be to the right. Right, so it's going to be this way. So we're going to shade into the right. Because of the equals to, we're going to put a bracket on that. And so as an interval, this is going to go from bracket 4/5, comma, to infinity. And this would be my domain for this problem. If they ask for it in interval notation, I don't have enough details here to know the way they want us to format the answer. It's possible they might just ask you to leave it like this, that x has to be greater than or equal to what? And you'll have like a blank here where you type in 4/5. So the way to find the domain on these problems, just to kind of break it down for you, because I know I talked about a lot of extra stuff here, is take whatever's inside the radical, if it's a square root. Now, if it's a cube root, there's no limitations, right? It could be positive or negative. It resolves to an answer regardless. So if it's a cube root, the domain is all real numbers. But if it's a square root, you take whatever's inside the square root, set it greater than or equal to 0, and then solve for x, and that'll tell you what your domain is. All right, the last page I have here, and I promised this earlier in the video, is I'm going to give you a list of numbers that I think you should memorize as we go through chapter 6. If you can memorize this set of numbers, maybe it's not numbers, but this set of results, it'll help you with resolving these square roots, these radicals, as we go through chapter 6. So these are all the numbers that we can take the square root of and have it simplify nicely. The square root of 4 is 2. The square root of 9 is 3. The square root of 16 is 4. Right? So for these numbers, they all have a nice simple origin from things being raised to the second power. So you should memorize these numbers here on the right-hand side and the corresponding answer. The square root of 64 is 8. The square root of 121 is 11. You should memorize these. It'll help a lot. These are the numbers that we can easily take the cube root of. And again, these are just the first few. There's more after this, but these are the ones I think you should memorize. The cube root of 8 is 2. The cube root of 27 is 3. The cube root of 64 is 4. The cube root of 125 is 5. Just memorize those. For fourth roots, we have a smaller list of numbers here. So the fourth root of 16 is 2. The fourth root of 81 is 3. The fourth root of 256 is 4. And then for fifth roots, these are the ones that you should memorize. The fifth root of 32 is 2. The fifth root of 243 is 3. All right, so that concludes the video on section 6.1, Introduction to Radicals.